Hello and welcome to another power system analysis class. In the previous class, we started with complex numbers, the polar form, and also phasors. We solved some practice problems. Today, we will continue that and solve some more practice problems. And we will also get into apparent power, real power, and reactive power, and how we can calculate that. I know that most of you are already familiar. This is just, again, a reminder because this is a very important part of this course. In this course, we mainly just deal with reactive power, real power, and how we model a power system and a grid. We solved some practice problems on RL circuits, and today, again, as I mentioned, we will continue with complex powers. So as you already know, power P is equal to VI. And V for an AC system is going to be V max or Vm cosine of omega t plus theta V. And IT is I max cosine of omega t plus theta I. Now, cosine of alpha, cosine of beta is equal to half of cosine of alpha minus beta plus cosine of alpha plus beta. So if we replace that, we can get PT, which is going to be half of V max, I max cosine of theta V minus theta I plus cosine of 2 omega t plus theta V plus theta I. I've already done the proof for this in measurement instrumentation, if you had measurement instrumentation with me. Now, the average power, PT, is going to be half of V max, I max, cosine of theta V minus theta I plus cosine of 2 omega t plus theta V plus theta I. The average power would be the area under the graph, or the integral, which is going to be 1 over t, the integral of 0 to t, pt dt, which is going to be half of V max, I max, cosine of theta V minus theta I. In other words, it's going to be the magnitude of V, magnitude of I, cosine of theta V minus theta I. And the power factor phi is going to be theta V minus theta I. So for a complex power S, what is S? Do you remember what is S? What do we call S? What is S called? It's our apparent power. What is the real power? P. And what is Q? Reactive power. What is the equation for S? S is going to be equal to P plus JQ. The real part of S is P. That's the reason we call it the real power as well. And the imaginary part of S is equal to Q, which is the reactive power. Now, the unit for real power is going to be watt, kilowatt, or megawatts. The unit for reactive power is going to be volt amp reactive, or kilovolt amp reactive, or megavolt amp reactive. And for complex power or apparent power, S is going to be equal to, the unit is going to be equal to volt amps, kilovolt amps, and megavolt amps. Now, the power factor PF is going to be the cosine of phi, and power factor doesn't have any units and doesn't have any units. And we have two scenarios. If the current leads the voltage, then the power factor is leading. If current lags the voltage, then the power factor is lagging. Do you remember the triangle for power? This is, again, very helpful, useful. This is S, this is our real power P, and this is Q. And if this is the imaginary, and this is the real axis. Now, again, we have a positive Q and a negative Q, so we can have a leading power factor or a lagging power factor. Now, what is this degree angle here? What is this called? Theta or phi. This is our, what is this angle? Yes, it's a power factor. Power factor. So power factor is going to be equal to tan inverse of what? The power factor degree. I'm gonna, let's say phi. So phi is going to be tan inverse of what? Real power, or in other words, phi would be equal to cosine inverse or arc cosine of what? Q over S or P over S? Who says it's Q over S? Who thinks it's P over S? This is cosine inverse again. Yes. And what is phi here? If I want to find phi, I want to find phi, I have a triangle. Forget about this part. I want to find phi. Phi here, what is it going to be equal to? Yes. So it's going to be cosine inverse of what? P over S. Thank you. Or phi is going to be tan inverse of Q over P, or sine inverse of Q over S. So if you have any of these, you can just simply use sine and cosines to be able to find it. Now, if Q is positive, do we have a leading power factor or a lagging power factor? So at this point, do we have a leading power factor or a lagging power factor? I'm going to draw the other one with blue. Positive, here we have negative Q. So when Q is positive, we have a lagging power factor. And when Q is negative, we have a leading power factor. When we have a leading power factor, do we have a capacitive or an inductive load? Capacitive, thank you. So we have a capacitive. And then when Q is positive, we have a what? Dot. That's the reason when we have an inductive load, we use a capacitor bank for power factor correction, okay? Again, if current leads the voltage, then power factor is leading. If current lags, so current is our benchmark. If it's leading power factor. If it's lagging power factor. Lagging power factor is an inductive load. Q is positive. Leading power factor, it's a capacitive load. And Q is negative. Now, in a complex power, pi and theta, we can write it as S cosine of phi and S sine of phi, as I mentioned in the previous one. Or in other words, positive, negative, the magnitude of S, square root of 1 minus PF square. So for example, a load draws 100 kilowatt with a leading power factor of 0.85. What phi or power factor angle Q and S has? So phi is going to be negative cosine inverse of 0.85. Why did we put negative here? Why? Yes, it's leading. Theta or phi here is negative and positive. So we have a leading power factor. That's the reason it's putting negative 31. And what is S is going to be equal to? It's going to be equal to power factor itself is going to be equal to P over S. P over S, cosine of P over S, and we have cosine of P over S, which is 0.85. So it's going to be 100 kilowatts over 0.85 gives us 117.6 kilovolts. Now to find Q, Q is going to be equal to S sine of theta, which is going to be negative 62.0 kilovolt amp reactants. Now, the power factor is between which numbers? What is the largest that the power factor could be, and what is the smallest that it could be? Yes, it could be between 1 and 0. Yes. What is the best scenario? What is the worst scenario? Best 0 is Y. Yes, perfect. Thank you. So if this is a power factor, we want S and P to be equal. So if S is equal to P here, and then theta is equal to what? Or phi? Phi is equal to 0. Yes. So cosine of 0 degrees is what? 1. Therefore, which is power factor. So power factor would be equal to 1, which is best case scenario. S is equal to P and Q is equal to what? 0. Thank you. And what is the worst case scenario, which never happens, is what? When theta is equal to what? Or phi is equal to 90 degrees. Cosine of 90 degrees is what? Sine of 90 degrees is what? 1. Therefore, S is equal to Q here. S would be equal to Q, and P would be equal to what? Which never happens. You already have a little bit of real power. So we want the power factor to always be close to what? To 1. So that's the reason we use a power factor correction system. So if we have a leading power factor or a lagging power factor, so imagine if you have a lagging power factor, and most time we have a lagging power factor. Why do we have a lagging power factor, by the way? Perfect. Inductive loaders, motors, transformers, thank you. And transmission lines as well. They have inductions as well. So in the power plant, you generate a power that's close, the power factor close to 1. But when you transmit it, what happens is you have inductive loads and you have transformers and motors and so on. And it causes the current to lag the voltage. And therefore, it causes a lagging power factor. Now, what we do, so again, we have a lagging power factor or positive power factor. What we do is we would add a power factor corrector, which is a capacitor bank at the consumer part to compensate for that. Why do we need to have the power factor corrector? Can't we just use the power like this? What problems does it cause? Yes? I'm sorry. Yes, it will be out of phase. But the thing is, we can say, okay, I can deal with this because I still have this much of real power. But yes, exactly. So the problem with reactive power is its cause is loss in the system, and that loss actually translates to heat, and it would damage the motor. So it would work, the motor would work initially, and you won't see any problem. But in long term, you would see that motor is heating up pretty quick, and it's going to damage the wiring, it's going to melt the wiring, and so on. So you may have an HVAC that the capacitor works, doesn't work for a while, you won't notice it, but after a while you would see the compressor is going to go out. So the problem is, again, long term, you're going to have a lot of loss and you're going to damage the system as well. That's the reason we put these capacitors. Usually in the AC motor, you can see that there is a capacitor on it, which is a compensator for that. Obviously, we can't get to a 1 power factor or a reactive power of 0, but we want that to be as close as possible to the power factor to 1, like 90, 98, something like that, 0.98 or something like that. Now, one important rule, we have the conservation of power. This is based on the Kirchhoff's current law, meaning the sum of real power into a node must equal to 0, and the sum of reactive power into a node must equal to 0 as well. And again, this is a direct consequence of the Kirchhoff's current law, which states that the total current into each node must equal to 0. For this rule, the conservation of power follows since S is equal to VI conjugate. Now, following the examples that I gave, let's solve another problem. Imagine we have this. We already solved for this. We have a load, and the load has a voltage of 100 with a degree of 30 degree. Resistance is 4. Inductance is 3J. And we want to find our complex or apparent power S. We want to find phi. We want to find the power factor. We want to find the apparent power in the resistor or the power consumed by the resistor. And we want to find the power consumed by the inductor as well. To do that, we need to find the real power consumed by the resistor. What about the reactive power consumed by the resistor? As we learned, it doesn't exist. We don't have, the resistor doesn't consume reactive power, and an ideal inductor doesn't consume real power. It's just reactive power, but obviously these in real world inductor still has a little bit of resistance in it. Now, I gave you the papers for this. This is going to be your quiz. You're going to have 2 questions, and this is going to be your first question. Again, please put your iPads and electronic devices away, and you just need basic Ohm's law to solve this, so no equations that are needed, and I'll give you 10 minutes to solve this. So for the online students, I would post another quiz, but yeah, I'm just gonna keep this running so you can see the solution as well for these questions. It's 100 with a degree of 30 degrees. So it's 100 with 30-degree angle. And from earlier, we found that I is equal to 20 with a degree of negative 6.9. So this is a continuation of the previous. But even if we didn't have that, we can easily use a KVL to find the current, but it's already given. So Okay, did you solve it or do you need more time? More time? Okay. Okay. So what is S? What did you find?
2 kilowatts.
Okay. And what did you find for phi? Okay. What about power factor? 0.92. Okay. What about PR?
That's just true.
Yes.
1.8 kilowatts.
What about you? Yeah. 1600 is correct. And what about S? What did you get? VI conjugate. What did you get for that? Okay. Okay, what about SL? Okay. What about QL? 200. Okay. So as you mentioned, S is going to be equal to VI conjugate. I is within negative 6.9 degree. So I conjugate would be positive 6.9 degree. Okay. And it's going to be V, which is 100 with a degree of 30 times 20 with a degree of 6.9. It's going to be 2 kilowatt with a degree of 2 kilovolt amp with a degree of 36.9. Now phi is 36.9. Power factor is going to be 0.8 lagging. And SR is going to be VRI conjugate, which again is going to be VR. VR is the voltage of the resistor. And for that, we use the IR. V is equal to IR equation. R is 2 and I is 20 with a degree of negative 6.9. We multiply it by the I conjugate, which is 20 with a degree of 6.9. And finally, PR is going to be I square R. Why? Because QR is going to be equal to 0. Therefore, it's going to be 1600, as you mentioned. And SL is going to be the apparent power of the inductor. The inductance of the inductor is 3J. The impedance of the inductor is 3J. Again, it's going to be VL, which is going to be IR times I conjugate. So it's going to be IZ, I'm sorry. Z is 3J, I is 20 with the degree of negative 6.9 times 20 with the degree of 6.9 degrees. And finally, QL is going to be 1200 volt amp reactive.
Conjugate,
I'm sorry.
20 at -6 degrees.
Yes, and the I conjugate would be 20 with a degree of positive 6.9 degrees.
Times the conjugate.
So here we ask for the VLIL conjugate, but because we wanted to find the conservation of the power. The question was about the conservation of the power. How much power is consumed in it, not how much power is passing through or made out of it. And if we wanted to find VLI, the only difference is going to be the angles. The amplitude is going to remain the same. And here we wanted QL, which is going to remain the same. It's not going to be different at all. Now, let's continue. So this lecture 3 is done. We're going to start with the lecture 4. And for lecture 4, I want you to keep those papers because we're going to have another question as well. We want to find now the power consumption in devices. As you know, resistors only consume real power. Inductors only consume reactive power. For resistive, PR or P resistive is going to be I square R, as you solved for the example for the first question. And inductors consume reactive power, and Q for the inductor is going to be I square of the inductor XL, which is its inductance. And for a capacitor, it only generates reactive power. So Q for the capacitor is going to be negative I of the capacitor square QC. Now XC, and XC is going to be equal to 1 over omega C. What is XL? Yes, omega L, or the inductance of the reactor, which is technically J omega L because it's a reactive power. So imaginary part is going to J omega L. Now, for Q of the capacitor, another equation that we can use is going to be negative V capacitor square over XC. And as we can see, we have defined XC as negative because, again, it's generating reactive power. We would assume it's generating reactive power. Now, this next example that I want you to solve, and again, 50% of the point here is just for attendance. The other 50% is for the questions. We want to solve the following circuit for current, voltage, and its apparent power or complex power. We don't have the voltage of the source, but we have the voltage on the inductor. It's 40,000 with a degree of 0 degrees. And I'm sorry, for the resistor, it's going to be 40,000 with a degree of 0 degrees. And for the inductance, it's going to be 5 plus J 40 ohms. And for the resistor, it's going to be 100 ohms. Again, we want to find the current I. You can usually easily do a KVO or Ohm's law to find that. We want to find the voltage V. And we also want to find the apparent power S. Again, I'll give you 10 minutes to solve this problem, and then I'll give you the results. Have you done? Are you done? Yes. Okay. So what is I? What did you find for I? So using Ohm's law, you can find I. It's going to be 40,000 with a degree of 0 degree divided by 100, which is the resistor, and it has a degree of 0 degree because it's a real. So this is going to be 400 with the degree of 0 degree. Amps. Now what about the voltage, V? So I can do a KVO, and if I do a KVO, it's going to be V minus the inductance times I minus the voltage of that resistor. In other words, I can write it like this: V, again, minus 5 plus J40 times the I minus 100 times I, or just write the 40,000 with a degree of 0 degrees. It's going to be equal to 0. Again, the current passing through this I is equal to the current passing through the inductor. They are in series, obviously. So V would be equal to 5 plus J40 times 400 with a degree of 0 degrees plus 40,000 with a degree of 0 degrees. So if we convert this, what did you get for this? Perfect. 45 with 21 degrees. And these are estimates, yes, just rounded. So you round it up and it's going to be 21 degrees. Kilovolts, yes. Okay. And what about S? S is going to be equal to VI conjugate, or VI. We want to find, again, the consumption power. So it's going to be equal to 44 point or 45. You round it up. So 45 kilovolts times with a degree of 21 degrees times 500 volts, 400 amps, I'm sorry, with a degree of 0 degrees. It doesn't make any difference. So what was this? What did you find for this? So if I want to round it up, it's going to be 18 with a degree of 21 degree megavolt amps. Again, we rounded up everything. So instead of here we have 44.9, it's going to be 45, and this one was 21 just by rounding it up. And this rounding up, it's going to be 18 with a degree of 21 degree. And if we want to convert it to a rectangular form, it's going to be 16.8 plus J 6.4 megavolt amps. Okay. Now, if we want to add additional reactive power load and solve it again, imagine we add an inductor in parallel with our resistor. And this inductor is J100 inductance. The impedance is J100. Now, what happens to the load? Now, the load that we have is a combination, and it's parallel. And if we want to find Z load, it's going to be the impedance of the resistor in parallel with the impedance of the inductor the way that we do that is it's going to be Z load, it's going to be ZR times ZL over ZR plus ZL gives us Z load, or Z of the inductance, if you don't want to confuse it. So again, if we want to find Z load, I'm going to show the Z of the inductance with Zi and the Z of the resistor with ZR. So it's going to be ZR, Zi, or ZR plus Z plus Zi. And by the way, this is the line and this is our load. Now, if we calculate for that, it's going to be 70 with a degree of 70.7 with a degree of 45 degrees. And the power factor, if we calculate it, it's going to give us 0.7 lagging. Now, I is going to be 564 with a degree of negative 45 degree amps. Again, using the Ohm's law, the previous one. Now we see that the current has increased a little bit. And the voltage is going to be 59.7 with a degree of 13.6 kilovolts, assuming that the voltage on the load remains the same, 40,000 volts or 40 kilovolts. Now, S is going to be 33.7 with a degree of 58.6 degrees megavolt amps, or in other words, it's going to be 17.6 plus J 28.8 megavolt amps. Okay. Again, this is just the final results. I would highly recommend that you go at home and solve it on your own as well. It's easy, just multiplying complex numbers and finding the final load. Now, this current is the current actually passing through the load itself, the total current that you have, and then it's going to pass through the transmission line or the inductance from the transmission. Now, some power system notations, I think we don't have enough time to continue this and finish it because this is, if I started, I have to go through all of it. But just for now, the power system components are usually shown as a one-line diagram. If we want to redraw the previous circuit, you can see we have a generator that we usually shown as a circle. Then we have transmission lines, which are shown as a single line, and the loads are shown as arrows. And here we can show how much power is generated with the generator. So for the previous one was 17.6. The previous example was plus J 28.8 megavolt amp, which you can see is the generator itself. So we are delivering this much power to the grid. And how much was the voltage for the generator? It was 59.7 kilovolts, so 59.7 kilovolts. And this is the power that it was consumed at the load part. And you can see that the power, and you can calculate the power that was consumed. And we can also show the difference between these two gives us the power that it was wasted in the transmission line. So the difference between 17.6 megawatts and 16 megawatts, it's 1.6 megawatts. Where does this come from? It comes from the real part of the transmission or the resistance of it, which is the 5 ohms that we have. And then we have the reactive part, which is the difference between creates the reactive, waste that we have in the line until it goes from the transmission to the generation to the load, and it's wasted in the transmission. I think it's enough for today. Next week, we will continue with the power system notations. I will post the first set of homework this week, and you're going to have 10 days to turn them in. Another thing that I want to mention is about your first exam. I was thinking the first week of March, if it's okay with you. We can have it on the first Tuesday or first Thursday. I think it's going to be better. because on Tuesday we can have a review session, and on Thursday we can have our first exam. Yes. I'm sorry, first Wednesday. I got confused. I'm sorry. So the first Monday, we're going to have our review session, and the first Wednesday of March, we're going to have our exam. I will post an announcement about that and the materials that are going to be on the first exam. It's going to be just reactive power, real power, the same examples that we solved. I'm going to change them a little bit. It's going to be the same. Please let me know if you have any questions. You can stop by my office or email me. Thank you so much, and I will see you next week. But also, I've